Hello everybody, today I will talk about another example of JFET or FET, which is called MOSFET or metal oxide semiconductor FET, field effect transistor. So let's see what is the structure of this MOSFET, and you will see that we have different kind of MOSFETs. The first one is called DE MOSFET. The structure is shown here. Okay, as you see here, we have N channel and we have P channel, similar to the JFET. So this is N doped material. This is substrate. Where is the gate? The gate is here. The gate. This is the gate, and we have this gold part here is metal. So we have metal. The source is connected to the channel through metal. The drain is connected to the ground to the channel through metal also, and the gate is connected here to metal, and there is a isolation or dielectric material here. This is a dielectric material. This is a gray area here. This is insulation layer, insulating layer, or dielectric material. Okay, so this is the structure of what we call it here, depletion enhancement MOSFET. Okay, the source, the symbol is given here for the DE MOSFET. Let's see what is the idea here. So, like JFET, okay, you see here we have also VGG connected. We have a negative, positive, so it is reverse bias connect to the gate, and we have also VDD, positive here, negative here. So it is exactly the same like the JFET. Okay. So now assume that we have we don't have VGG. There's nothing here. This is 0. So what will happen? That we'll have some electrons here. The electrons are moving. They will force the current or electrons to move from the source to the drain through the channel. Okay, so this will happen when VGG equals 0, which make the gate source voltage equal 0. So this is again exactly the same like the JFET. This is exactly as if I am reviewing the JFET. Okay, and then because of course we have assume that we have our VGG here. This one is negative, so this one will be negative here. Okay, this is maybe a little bit the difference, little bit. So here, but the function is the same until now. So we have negative connected to this metal. So this negative will access this conductor here, metal, and the dielectric material and the N channel will act as capacitor. So when it acts as a capacitor, when you have negative charge here, this will have we will have positive charges on the other side. This is the idea of the capacitor. When you have apply voltage on a capacitor, 2 plates, if you have a negative charge here, you will have a positive charge in the other plate. So in this case, we have positive charges here. When we have positive charges in the N channel, this means that you will fill, you will have holes like positive and negative. They will react to each other. So in this case, you are filling this position here with the depletion region. Okay, so at the beginning you do not have any positive charges here, so you have this all in the channel in material electrons. So you have a lot of electrons here, but when you apply this voltage, okay, what will happen? That we will have electrons here or negative charges here, and you will have positive charges here. So positive charges will work with the negative charges. So exactly like if you have a hole and electrons. So in this case, this will decrease the number of electrons because you are increasing number of positive charges. Imagine, for example, that the electrons are 100. For example, of course, this is not the right number. Okay, and you have it in a place, for example, and then you add to this this place you have for example 20 holes. So the electrons will fill these holes, So what are the remaining free electrons to move? 80. Okay, this is what happened. At the beginning, we have just electrons in the inner channel. Okay, but when you add positive charges, so exactly as if you add holes, then the electrons will fill these holes. Then you will have the remaining electrons that can move from the source to the drain are less, and so on. And this is explained here, but we call it here, by what we call it a depletion region. Depletion region. So when you apply increase more this VGG more, then what happens that you increase this depletion region, and in this case you decrease the electrons that can move, as if you are decreasing this area here. So in this case you're decreasing the current. You can decrease the current. And at certain voltage for VGG, you will block this area completely. Then you will have to have no current completely. Okay, between from the source to the drain, electron current. So it is exactly the same like the GFET. I really don't know until now. I don't know what's the difference here between MOSFET and GFET. Let us see. Okay. So now, when VGS increase, the gate or N channel act as a two-plate capacitor, as I said, with the electric material in the middle. So the negative charges on this part here, the gate plate, leads to positive charges on the channel here. This will increase the depletion region, of course. Okay, and when we have more VGS, the more depletion region and less ID, drain current, until it becomes zero. This when VGS equal VGS off. So this is what we call it here, depletion mode. So now this is the same like GFET. So what is that difference? Okay, this is a question here. What's the difference? The difference is in the other side. If we reverse this voltage for GFET, you have to have a reverse bias only. So you have this one. You must have this one negative and this one is positive. Okay, but if you reverse this voltage, then in this case you will have a forward bias between the gate and the source. If you have a positive here and negative here, you have a forward bias between the gate and the source, and you lose the control. You cannot control the current in the GFET. Okay, so what if we do it here? What will happen? Imagine that this is positive, this one is positive, this one is negative. Now, if this is positive, okay, this is not working here like a forward and reverse bias now. So now we have a positive here. So if we have a positive here, then we'll have negative here. Okay, so negative and the n type is also already negative. This means that you are reading the negative, increasing the negatives. Then actually you are increasing the number of electrons. So when you increase the number of electrons, in this case you are increasing the current. So if this one is positive, this voltage is positive here, then in this case, the more positive this voltage, the more current you can have. Okay, so here this work if this is negative or positive. If it is positive, you can even enhance or increase the current, I drain. If it is negative, you can control it. You can decrease it until you stop it completely. So this is the main difference between the MOSFET, DE MOSFET, and the GFET. So let's see if this is what is written here. So the difference between DE MOSFET and GFET is the positive VGS. In GFET, this would forward bias the junction, the source gate junction, and you will lose the control over the GFET. But in DE MOSFET, it will reverse the polarities associated with what? With the gate and the channel. Please, as I mentioned before, the gate will be positive. In this case, the channel, which is the other plate of the capacitor, will be negative. Negative means you add more electrons inside the channels. So again, before the other example, if you have a place where you have 100 electrons, for example, if you add 20 electrons, then the total will be 120. So in this case, you have more electrons to move from the source to the drain. So this will create more negative charges in the channel. Thus, positive VGS enhance the channel conductivity by increasing the current, of course. Okay, this mode is called enhanced mode. So this also means that the IDSS is no longer the maximum. In JFET, IDSS was the maximum current when VGS equals 0. Here, no. If VGS is positive, you can increase the current more. Okay. The equation is almost the same. There is no difference here. You see the current ID equal IDSS, which is the saturation current, time 1 minus VGS over VGS off. This is a voltage. When VGS equals this voltage, then it will be the current ID will be 0. Okay, and this is a symbol, as I mentioned before, for N channel and P channel. And this is the same, exactly the same equations. So if we have even the same model, so if we have, for example, a circuit like this for the MOSFET, and we have IDSS equal 12, VGS equal -3, and IG equals 0, then we need to find ID, VDS, and GM0. Okay, GM0 is this one here, but let us see first ID. ID is here. So IDSS equal what? Equal -12 milli. 1 minus VGS. What's VGS in this case? VGS is the voltage between the gate, G, and the source. Okay, the gate and the source, which is the same here because source is connected to the ground, so it is the same voltage between the gate and the ground here. Okay, so this is equal to this VGG, and the VGG here is what? VGG is 0. Yeah, VGG here is 0. This is 0. Okay, so VGS equal also 0. VGS equal 0. Okay, because you don't have current here. IG equals 0. So the voltage between this one and this one is the same like the source because you don't have current, and the source is 0, so 0. So actually, you do not have this part here. Then ID equal what? IDSS. That's it. Which is 12 milli. Okay, and then we need to find VDS. VDS, as I said, you can calculate it from here or from here. VDS is this voltage here equal this 20 volt minus ID time 1 kilo ohm. That's it. So 20 volt minus ID time 1 kilo ohm. That's it. GM0, you use this equation here. It is -2. IDSS, we have it, which is 12 milli. VGS off equal -3. Okay, so this is GM0. There it is. That's it. Very simple. The problems in DMOSFET and JFET are so simple.